Inspecting piecewise functions for differentiability. I would like to recall that if a function is differentiable at x equals c, it must be continuous, it must have a limit at x equals c. It means that if we have a piecewise function and c is a suspicious point, we have to check all the following. 1. We have to check that the limit exists by checking the two-sided limits that they exist and equal. 2. We have to check that the function is continuous. This is done by checking that the limit at x equals c approaches to f of c. And in addition to that, we have also to check that there is no sharp corner at x equals c and no vertical tangent line at x equals c. So the function is differentiable at x equals c if 1. The limit from the right exists. 2. The limit from the left exists. 3. The limits from the right and the left are the same. We will call L their common value. This implies that the limit of the function when x approaches c equals L. Now we have to do step 4. We have to show that L, which is the limit of the function when x approaches c, equals the value of the function at c, which is f of c. 1, 2, 3, 4, to recall, implies that the function is continuous at x equals c. Now we have to add step 5. We have to show that the derivative from the left and from the right of x equals c are the same, and also we need to show that this derivative is finite. If the derivative of the function from the right does not equal to the derivative of the function from the left, then the function is not differentiable at x equals c, and there is no need to check any other step. Example: here is a piecewise function f(x), and we want to inspect the function for differentiability at x equals 2. Please note that it is clear that the function is differentiable for all values except maybe at x equals 2, because when x is not 2, the function is just a polynomial function which is differentiable everywhere. We are going to do all the steps. Step number 1. The limit of the function from the right of 2 is 2. The limit of the function x approaches to 2 from the left is also 2, because we are using x to the power of 2 minus x. In 3, we check that the right and the left limits are exactly the same. They are. And the common value is 2, which means that the limit of the function when f(x) approaches 2 is 2. Step number 4. The limit which equals 2 is indeed f of 2. We now conclude that f is continuous at x equals 2. Now step 5. The derivative of the function from the right is 1, because on the right the function is x and the derivative of x is 1. The derivative of the function from the left is using the branch x to the power of 2 minus x. The derivative of x to the power of 2 minus x is 2x minus 1. Now we have to substitute 2, and we get that the derivative from the left is 3. Definitely 1 is not 3. It means that the slope at x equals 2 changes from 3 to 1. We're definitely getting here a corner, and we conclude that the function is not differentiable at x equals 2. Now we are going to do this in a different way. We are going to start with step 5. Here is the function. Now we are going to differentiate the two branches. When x is less than 2, it's the derivative of x to the power of 2 minus x, which is 2x minus 1. When x is more than 2, it's the derivative of x, which is 1. We cannot include 2 when we do something like this, because 2 is always a suspicious point. Now it's easy to calculate that the derivative of the function from the left of 2 is 3, and from the right is 1. And we get again that the slope at x equals 2 changes from 3 to 1, and there is a corner. We conclude again that f is not differentiable at x equals 2. Be careful. If step 5 fails for x equals c, then the function is not differentiable at x equals c, and we are done. In other words, if the left and the right derivatives at x equals c are not the same or infinite, then f is not differentiable at x equals c. But the opposite is wrong. If in step 5 we will get that the derivative from the right and the derivative from the left are exactly the same and finite, then the function is differentiable at c only if it is continuous at x equals c, which means that this is not enough. Here is an example. If we check only step 5 in this graph, we will get that the slope of the tangent line from the right and from the left of x equals c have exactly the same slope. There is no corner and there is no change in the slope, but you can see that this function is not continuous at x equals c, and that's why it's not differentiable at x equals c, in spite of the fact that step 5 will be totally okay. The conclusion is that if you want to start with step 5 and you get that the slope from the right and the left are exactly the same, this is still meaningless unless the function is continuous at x equals c, and you will have to show that. Here's another example, and here of course we want to inspect the graph for differentiability at x equals 1. Let's start with step 5. Here is the derivative at 1 plus, which means from the right of x equals 1. We get 1 because it's using the branch when the function equals x and the derivative of x is 1. What about the other side of 1? From the left, we are using the branch of x to the power of 2 minus x. We differentiate that and we get 2x minus 1. And when x equals 1, it is 1. Definitely not a corner. And definitely there is no change in the slope when x equals 1. But we still have to show that the function is continuous, because otherwise this is meaningless. Here is the graph of the function. When you have the graph, you see immediately that the function is not continuous at x equals 1, and then, by a theorem, it cannot be differentiable at x equals 1. The reason for this specific function to be not continuous at x equals 1 is because the right and the left limits are not the same. Obviously, we have this theorem, or this was a conclusion from a theorem, that if the limit does not exist, then the function is not continuous, and then it cannot be differentiable at x equals c.